in the vast, whispering silence between the stars, where light takes centuries to bridge the gap between suns and the darkness, is so profound it feels like a physical substance. There exists a pattern. This is not the chaotic, seething noise of the cosmos, the pops and crackles of dying stars, or the low-frequency groan of merging galaxies. This is something else entirely. It is a signal, a precise, repeating pulse of radio waves, cutting through the interstellar medium with a regularity that is, in all the known universe, deeply unnatural. For 16 days, the silence holds, a deep and patient quiet in one particular slice of the sky. A quiet so complete it convinces the listening instruments that perhaps they had imagined the last burst, that it was a ghost in the machine, a flicker of cosmic static. And then, on the 17th day, it returns. Not once, but in a rapid, staccato series of brilliant flashes, each lasting mere milliseconds, yet containing more energy than our sun releases in 80 years. It erupts, announces its presence with undeniable clarity, and then, just as suddenly as it arrived, it vanishes again. This cycle, this celestial metronome, ticks on with a patience that spans millions of light years, a 4-day window of activity, followed by 12 days of profound silence, repeating every 16.35 days with a precision that feels almost mechanical. This is the story of FRB 180916, J158 plus 65, a fast radio burst that taught us the universe is capable of keeping time. To understand the weight of this discovery, the profound mystery and subtle terror of a repeating clock in the void, we must first step back, away from the specific coordinates in the constellation Cassiopeia, and sink into the deeper history of cosmic listening, into the moment humanity first began to hear the universe, not as a silent panorama of light, but as a symphony of invisible, raging energies. It begins, as so many stories of cosmic mystery do, not with a planned search for the unknown, but with an accident. A piece of data so strange it was initially dismissed as terrestrial interference, a lunchtime microwave oven near a telescope in Australia. The year was 2007. An astronomer, Duncan Lorimer, was sifting through archival data from the Parkes radio telescope, recorded 6 years prior, searching for the faint signatures of distant pulsars. What he found, buried in the magnetic tape, was a single, colossal spike of radio emission, a burst that lasted 5 milliseconds and seemed to have traveled across an immense gulf of space, carrying with it the imprint of its journey through the ionized plasma between galaxies. This was the first fast radio burst, later named the Lorimer burst, and it presented an immediate and profound puzzle. Its dispersion measured the telltale smear of its signal caused by electrons in its path, suggested an origin far beyond our Milky Way, perhaps billions of light years distant. Yet, for a source so distant to appear so bright, it had to be releasing an almost unimaginable amount of energy in the blink of an eye. The astronomical community was skeptical. Such a thing seemed impossible, a flaw in the data, a local artifact. For years, the Lorimer burst stood alone, a cosmic unicorn, its very existence debated. But then, another was found, and another. The field of radio astronomy, with its ever more sensitive arrays and sophisticated software, began to catch these ephemeral events, these cosmic mayflies that lived and died in milliseconds. Each new detection was a solitary event, a one-off explosion in a distant galaxy, which only deepened the mystery. What catastrophic, one-time event could produce such a brilliant, fleeting flash? Theorists offered a menagerie of possibilities. The final, screaming death cry of a neutron star collapsing into a black hole. The cataclysmic merger of two incredibly dense stellar corpses. Or perhaps the violent tantrum of a highly magnetized star? A magnetar, undergoing a starquake that would crack its crystalline crust and release a tsunami of magnetic energy. These models were compelling, but they shared a common, implicit assumption. These bursts were the final, destructive acts of stellar beings, never to be repeated from the same source. The universe, in this view, was filled with unpredictable, brilliant flashes of radio light, each a funeral pyre for a unique and exotic object. This was the state of understanding a field built on singularities until 2016, when everything changed. The Arecibo radio telescope in Puerto Rico, that great bowl nestled in a karst sinkhole, detected something that shattered the single burst paradigm. FRB 121102 did not flash once and vanish. It flashed again and again. It was a repeater. This discovery alone was a monumental shift, proving that at least some sources of these bursts could survive their own apocalyptic emissions, that the engine powering them was not purely destructive, but could fire again and again. The repeater localized to a tiny, turbulent dwarf galaxy 3 billion light-years away, a place of frantic star formation, a nursery for the very neutron stars and magnetars suspected to be the culprits. The mystery had narrowed, but it had also deepened. We now knew repeaters existed, but their repetitions were erratic, unpredictable, a stutter of cosmic static with no discernible rhythm. They were like a faulty lighthouse, flashing at random intervals, governed by a chaos we could not decipher. This was the landscape into which the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, was born. CHIME is not a traditional steerable dish. It is a radical, fixed array of 4 half-cylinders, resembling enormous snowboarding half-pipes, stretched across a rural landscape in British Columbia. Its design allows it to stare, unmoving, at a vast swath of the northern sky every day, as the rotation of the Earth sweeps the heavens above it. It is not a telescope that points. It is a telescope that listens constantly to a wide band of radio frequencies. This made it, almost by accident, the perfect instrument for catching the transient, unpredictable whispers of fast radio bursts. And on a routine day in 2019, as its correlators sifted through the river of data flowing from its antennas, it caught something extraordinary. It was a new repeater, designated FRB 180916, J158 plus 65. What set this one apart was not initially its repetitions, but the clarity with which CHIME could observe them. The burst sequences were bright. They were frequent within their active windows, and they left a clean, precise fingerprint in the data. As the months passed and the detections piled up, a graduate student on the CHIME team, working through the timestamps of each flare, began to notice a curious pattern. The dates of the activity seemed to cluster, then fall silent, then cluster again. When she plotted them against time, applying statistical tests, a shape emerged from the noise that was both simple and breathtaking, a perfect periodic curve. The source was active for roughly 4 days, during which it might produce several bursts per hour or remain quiet for long stretches within that window, and then it would shut off completely for the next 12 days. This 16.35-day cycle was not a subtle statistical hint. It was a stark, repeating structure in the behavior of an object billions of light years from Earth. For the first time, humanity was not just witnessing a repeating cosmic signal, we were witnessing a cosmic signal that kept a schedule. The immediate effect of this discovery was a profound and quiet disorientation in the astrophysical community. The universe in all its chaotic, entropic glory is not a place of clean, regular cycles on such short, human comprehensible timescales, especially not from an engine of such ferocious power. The orderly orbits of planets, the steady spin of pulsars, these are the rhythms of gravity and rotation. But this was different. This was the rhythm of emission, of violence. It pointed unequivocally to a system in motion, an engine whose fury was being modulated, gated, or shadowed by something else orbiting around it. The 16-day period was a clue written in time itself, a direct tracer of the geometry and mechanics of a system so remote its light had been traveling through the void since before multicellular life existed on Earth. The quiet, patient listening had paid off, not with a shout, but with a ticking. The identification of this 16-day cycle transformed the mystery from a question of what could produce such immense energy to a question of how such a process could be so precisely regulated. It was as if we had been listening to a distant, storm-racked sea, hearing only the occasional tremendous crash of a rogue wave, and had suddenly discerned, beneath the chaos, the steady, predictable rhythm of the tide. The tide, in this cosmic analogy, implied a gravitational hand, an unseen companion whose orbital dance periodically allowed, or perhaps triggered, the eruptions we observed as bursts. The theoretical machinery of astrophysics, which had been whirring with models of isolated cataclysmic events, now had to be reconfigured to accommodate a clockwork duo. The most immediate and compelling framework to emerge was that of a binary system, a pair of celestial dancers locked in a gravitational embrace, with the source of the bursts almost certainly a neutron star, the hyperdense, city-sized remnant of a supernova orbiting a companion. The 16.35-day period would then simply be the orbital period of this deadly waltz. But what kind of companion could impose such a strict schedule on such a violent phenomenon? The possibilities sketch themselves out like chapters in a catalog of stellar oddities. One scenario involved a massive OB-type star, a brilliant blue giant burning its hydrogen fuel with a profligate intensity, driving a powerful stellar wind out into space. In this model, the neutron star, in its elliptical orbit, would plunge through the thick, gusting wind of its companion every 16 days. As it plowed through this torrent of charged particles, the interaction, a shock front forming where the neutron star's own magnetosphere met, the stellar wind could act as a natural particle accelerator, triggering the conditions necessary for a fast radio burst. The 4-day window of activity would correspond to the perilous passage through the densest part of this wind, a kind of celestial storm season, after which the neutron star would emerge into the relative calm of a pastron, its orbit's furthest point, for the remaining 12 days of silence. This was an elegant idea, rooted in known physics of wind-fed pulsars, but it had its tensions. The bursts themselves, with their millisecond durations and immense brightness temperatures, demanded a coherent emission process, a kind of laser-like maser action on a galactic scale, which was difficult to square perfectly with the turbulent, chaotic environment of a stellar windshock. Another, more serene, yet more ominous possibility: place the neutron star in orbit around a black hole. Here, the modulation would not be caused by an immersion in stellar material, but by a periodic eclipse. If the neutron star were a magnetar, a neutron star with a magnetic field 1,000 trillion times stronger than Earth's, its bursting activity might be constant, a relentless fury. But if it were orbiting a black hole surrounded by a dense, swirling accretion disk of gas and dust, our view of its outbursts would be periodically blocked as the neutron star passed behind this opaque screen from our perspective on Earth. The 4-day active window would be when it was clear of the disk, its signals flying unimpeded across the cosmos. The 12 days of silence would be its long eclipse behind the shrouding material of its dark companion's feast. This model had a chilling, geometric beauty, explaining the sharp-on divided by off transition with a simple line-of-sight obstruction. Yet, it required a specific and perhaps finicky alignment of the orbital plane to our vantage point. A third candidate emerged from the cooler, longer-lived stellar population, a main sequence star, like our own sun, but with a highly active magnetic personality. In this model, the neutron star's orbit carries it through the extended corona of its companion, a realm of tangled magnetic fields and superheated plasma. The reconnection of these fields, a sudden, violent snapping and rearranging of magnetic lines, could inject energy into the neutron star's magnetosphere, tipping it over an instability threshold and unleashing a burst. The cycle would then be governed by the geometry of magnetic interaction, a dialogue between two powerful magnetospheres. Each of these models painted a vivid, dynamic portrait of a system under extreme stress, a relationship defined by periodic violence. But to move beyond speculation, the burst source needed a home, a specific galactic address. The repeating nature of FRB 180916 was the key that unlocked this door. Because it repeated, astronomers could point the world's most powerful interferometric telescopes, networks of dishes spread across continents that work in unison, to achieve incredible resolution toward its location during its predicted active window. Wait. In early 2020, using the European Very Long Baseline Interferometry Network, a team succeeded in pinpointing the burst's origin with sub-arcsecond precision. They traced it not to the chaotic heart of a distant dwarf galaxy, like the first repeater, but to a surprisingly familiar environment, a spiral galaxy, much like our own Milky Way, named SDSS J15800,28 plus 654,253, located a relatively nearby 500 million light-years away. This proximity itself was a revelation. It meant the burst's intrinsic energy, while still staggering, was orders of magnitude lower than that of the more distant repeaters, suggesting a possible continuum of burst strengths in the universe. More importantly, the precise localization allowed the Hubble Space Telescope to turn its unblinking eye on that tiny patch of sky and resolve the specific neighborhood within that spiral arm. The source was not located in the brilliant, star-forming nebulae of the galaxy's spiral arms, nor in the ancient, quiet stellar populations of its halo. Instead, it resided in a region of modest star formation, a suburban stellar environment. This crucial detail argued strongly against the massive OB star companion model. As such short-lived, titanic stars are found only in the densest, youngest stellar nurseries. The environment was too quiet, too ordinary, for such a dramatic partner. The binary black hole eclipse model, while not ruled out, began to seem less likely without the clear signature of an active galactic nucleus or other signs of a feeding supermassive black hole in that locale. The data was gently, but insistently, pointing toward a more subdued stellar companion, perhaps a low-mass star or even a white dwarf. This environmental context forced a refinement of the theoretical picture. The emerging favored model began to coalesce around a neutron star, likely a magnetar, in a moderately eccentric orbit with a massive, middle-aged star. This companion star, while not a blue giant, could still possess a significant stellar wind and a substantial magnetic field. The interplay during periastron, the closest approach in the orbit, could be sufficient to perturb the magnetar's already unimaginably tense magnetic fields, stored like twisted springs of energy in its solid, crystalline crust. The perturbation could trigger a starquake, a cracking of the neutron star's surface that releases a cataclysm of magnetic energy, accelerating particles to near-light speeds in a process that generates a coherent beam of radio waves, the fast radio burst. The 4-day active phase corresponds to the period of greatest tidal and magnetic stress around closest approach. As the magnetar swings away, the stresses relax, the system settles, and the bursts cease until the next intimate, violent dance. This model elegantly ties the clockwork period to orbital mechanics, the active window to a phase of peak interaction, and the burst mechanism to the known, though extreme, physics of magnetar hyperflares. It paints the repeating FRB not as a random catastrophe, but as a symptom of a relationship, a predictable outburst in an ongoing, dynamic tension between two celestial bodies. Yet, even as this narrative solidifies, the detection of this rhythm has opened a far wider door of implication. For if one repeater has a period, how many others might? The search is now on for hidden cycles. In the data of other repeating FRBs, a patient sifting of timestamps for the subtle signatures of celestial clocks. Some may have periods of days, others of years. Each discovered rhythm will be another coordinate in mapping the diverse population of these systems. Another clue to the universal conditions that can give rise to such precise, yet such furious, cosmic beacons. The 16-day signal is more than a single mystery solved. It is a template, a proof of concept that in the seeming chaos of the high-energy universe, there can be order, a rhythm we can learn to predict, and in that prediction, begin to truly understand. With the rhythmic source now placed in its galactic context, a quiet suburb of a spiral galaxy, the investigation turns inward to the heart of the engine itself. To comprehend the scale of violence contained within those milliseconds of radio light, one must venture conceptually into the realm of the neutron star, and specifically, its most ferocious variant, the magnetar. Imagine the core of a star 10 times more massive than our Sun, a sphere of incandescent plasma millions of kilometers across, collapsing under its own weight in the final seconds of its life. The outer layers rebound in a supernova explosion of unimaginable brightness, visible across galactic distances, while the core, compressed beyond the limits of atomic structure, continues to implode. Electrons are crushed into protons, forming neutrons, until the entire mass of a star is packed into a sphere no wider than a city. The density is such that a single sugar cube-sized fragment of this material would weigh as much as a mountain, its very atoms dissolved into a quantum soup of neutrons. This is a neutron star, an object where gravity has triumphed over almost every other force. But for a subset of these stellar corpses, the dying star's magnetic field, trapped and concentrated during collapse, undergoes a transformation that defies everyday intuition. The magnetic field, a relic of the progenitor star's dynamo, is frozen into the collapsing plasma and amplified to levels that border on the absurd. The result is a magnetar, a neutron star with a magnetic field a quadrillion times stronger than Earth's. To be near such an object is to enter a realm where physics is distorted. The field is so powerful it can polarize the vacuum of space itself, making empty space birefringent, and can rip apart molecules from a distance of 100,000 kilometers. The magnetar's crust, a crystalline lattice of iron nuclei 10 billion times stronger than steel, is under perpetual intolerable strain, bent and stressed by the intense magnetic fields threading through it. It is in this state of perpetual quivering tension that the mechanism for a fast radio burst likely resides. The prevailing model for the burst from a source like FRB 180916 involves a starquake. As the magnetar orbits its companion, the external gravitational and magnetic nudges, especially during the close approach of its 16-day cycle, add incremental stress to this already critically loaded crust. Like a tectonic plate on Earth, the crust can withstand the strain only up to a point. When that point is exceeded, it cracks. But this is no earthly tremor. The energy released in a magnetar starquake is equivalent to a magnitude 30 or greater earthquake, enough to vibrate the entire star, a phenomenon observed as a glitch in its otherwise perfectly periodic spin. The sudden rearrangement of the crust releases pent-up magnetic energy in a cataclysmic reorganization of field lines, a magnetic reconnection event of cosmic proportions. In a process that is still not fully understood, but is akin to a supercharged version of solar flares, the reconnection accelerates electrons, and possibly positrons, to velocities extremely close to the speed of light within a plasma bathed in the magnetic field. These ultra-relativistic particles, moving along curved magnetic field lines, emit radiation in a tightly focused, coherent beam via a process called synchrotron maser emission. Essentially, the conditions are so extreme and orderly that the particles radiate in lockstep, like a laser, producing a spectacularly bright, narrow-band pulse of radio waves. This beam, focused by the magnetar's global magnetic geometry, sweeps across space like a lighthouse beacon. If Earth lies in its path for that fleeting millisecond, our telescopes register a fast radio burst. The sheer energy required is staggering. In those few milliseconds, the magnetar can release more energy than our sun does in 80 years. Yet, because the energy is channeled into a coherent beam and focused into the radio part of the spectrum, and because the magnetar itself survives the event, the process can repeat. This model elegantly explains the repeater phenomenon and, when placed in a binary system, provides a natural trigger for the quakes in the form of periodic tidal stresses. However, the detection of the 16-day period introduced a new layer of subtlety. The bursts themselves are not uniformly distributed within the 4-day active window. They cluster, sometimes appearing in rapid succession over a few hours, then falling silent for a day within the active phase, only to flare again. This suggests that the crust, once stressed to its breaking point, may fail in a series of aftershocks, or that the magnetic reconnection process occurs in bursts within a larger, unstable plasma region. It paints a picture of an engine that is not simply switched on and off, but one that sputters, crackles, and releases its energy in discrete packets once the overall conditions for instability are met. This variability within the period is a crucial diagnostic, a fingerprint of the microphysics happening on the magnetar's surface and in its magnetosphere, far beyond our ability to directly image. The binary modulation provides the schedule, but the burst production within that schedule is governed by the complex, chaotic-seeming dynamics of plasma physics and crustal mechanics. Understanding this requires looking beyond our single, rhythmic example to the broader population of FRBs. The discovery of FRB 180916's period immediately prompted a re-examination of data from the original repeater, FRB 121102. Could it, too, have a hidden rhythm? Initial analyses suggested no clear periodicity on timescales up to 160 days. But the search continues, with more sophisticated algorithms sifting through its erratic bursting patterns. This contrast is profoundly informative. It suggests that not all repeating FRBs are the same. Some, like 180916, may be in tidy binary systems where a companion provides a regular trigger. Others, like 121102, may be isolated magnetars, whose bursts are triggered by internal crustal evolution or perhaps by the fallback of debris from its supernova, leading to a more random, storm-like bursting pattern. Still, other repeaters may be in different types of binary systems, with different orbital periods, eccentricities, or companion types producing different modulation patterns. The single 16-day clock has revealed not a monolithic answer, but a diversity of pathways to the same phenomenal endpoint, a brilliant, coherent radio flash that can be seen across the universe. This diversity extends to the one-off, non-repeating FRBs as well. The periodic model does not necessarily apply to them. They may indeed be the final catastrophic events originally imagined, the merger of two neutron stars, the collapse of a neutron star into a black hole, or the explosive death of a highly magnetized star in a Blitzar event. The universe, it seems, has devised multiple methods for producing these brilliant radio transients. The repeating periodic ones, like FRB 180916, offer us a rare, stable laboratory. Because we can predict when they will be active, we can marshal other telescopes to observe them across the electromagnetic spectrum. The search for multi-wavelength counterparts, a flash of X-rays, a glimmer of visible light, a hint of gamma rays accompanying the radio burst, has become a primary endeavor. A simultaneous detection in another band would be a Rosetta Stone, unlocking the exact physical processes at play. For instance, magnetar flares in our own galaxy are prolific emitters of hard X-rays and gamma rays. If a fast radio burst from 500 million light-years away were accompanied by a similar high-energy signature, it would cement the magnetar connection beyond doubt. As of now, no such unambiguous counterpart has been found for an extragalactic FRB, but the search is young, and the predictions provided by the 16-day cycle make the hunt infinitely more targeted. We can point the Chandra X-ray Observatory, or the Swift Gamma Ray Telescope at the right place, at the right time. And wait, this transition from stochastic discovery to guided observation marks a sea change in the field. We are no longer simply catching cosmic lightning in a bottle. We are learning to predict where and when the storm will erupt. The predictable rhythm of FRB 180916 does more than illuminate the mechanics of a single distant object. It casts a long, probing shadow back onto our own cosmic neighborhood, inviting a quiet but profound reassessment of the risks and wonders that might lie hidden within the Milky Way. If such an engine can exist in a tranquil spiral arm of a galaxy 500 million light-years away, there is no reason, statistically or physically, why similar systems could not be nestled within the dusty spiral arms of our own galaxy, ticking away with their own periods, their own cycles of violent magnetic spring-loading and release. This realization brings the mystery from the abstract, cosmological distance into a realm of tangible, local possibility. Our galaxy is known to host magnetars. We have cataloged over 24 of them, all within roughly 20,000 light-years. These galactic magnetars are not silent. They occasionally produce giant flares, events that for a fraction of a second can outshine the entire galaxy in hard X-rays and gamma rays. The most famous of these, the 2004 flare from SGR 1806-20, released more energy in 1/10 of a second than the Sun has emitted in 100,000 years. And its gamma-ray pulse was powerful enough to significantly ionize Earth's upper atmosphere from 50,000 light-years away. Yet, despite their ferocity, these galactic magnetar flares have not been definitively linked to a fast radio burst. They are brilliant in the high-energy spectrum, but the coherent, brilliant radio flash has not been conclusively seen accompanying them from within our galaxy. This presents a fascinating puzzle. Are the extragalactic FRBs, especially the repeating periodic ones, a different breed of magnetar outburst? Or is it simply a matter of geometry? The radio beam from our galactic magnetars is so narrow that it has not yet swept across Earth during a flare. Or perhaps the local environment around a young, isolated magnetar, still embedded in the supernova remnant of its birth, is different from that of an older magnetar in a binary system, stifling the coherent radio emission? The discovery of the periodic repeaters suggests another avenue. Perhaps the galactic magnetars we observe are the solitary, randomly flaring kind, like FRB 121102. The binary, periodically triggered kind, like FRB 180916, might be older systems that have migrated from their birth clusters, their binary companions having survived the supernova, and they are simply waiting to be found. A search for periodic radioactivity from known galactic magnetars or from unidentified X-ray sources is now a logical, though immensely challenging next step. The implications of finding such a periodic, bursting source within our galaxy would be monumental. Beyond the sheer scientific value of having a front-row seat to the engine, it would allow for an unprecedented level of diagnostic detail. We could measure the binary orbit with exquisite precision through Doppler shifts. We could study the companion star spectroscopically. We could deploy neutrino and gravitational wave detectors in the hope of catching a signal from the starquake itself, feeling the vibration of spacetime from the crustal fracture. A galactic periodic FRB source would become the ultimate laboratory for extreme physics. This line of thought leads inevitably to a quieter, more speculative question, one that has hovered at the edges of the FRB mystery since the first repeater was found. The question of artificiality. The human mind, trained by a century of science fiction, cannot help but notice the eerily precise, information-rich nature of a repeating periodic signal from deep space. The 16-day period itself is devoid of message. It is simply a cycle, but its very existence demonstrates a regularity that in our limited experience is often associated with technology. The pulsars themselves, when first discovered in 1967, were briefly labeled LGM-1 for Little Green Men due to their stunning regularity. We now understand pulsars as natural, rotating lighthouses. The repeating FRB, especially a periodic one, is a more complex phenomenon, but the scientific consensus, built on the solid bedrock of magnetar physics and binary dynamics, finds a compelling natural explanation. The power requirements for an artificial beacon of such scale are almost incomprehensible, and the lack of any detectable information modulation in the bursts. They are simple, band-limited pulses, argues against an engineered communication signal. Yet, the consideration is not entirely dismissed out of hand by all. It serves as a useful intellectual exercise in the limits of our discernment. As the astronomer Carl Sagan famously noted, absence of evidence is not evidence of absence. The true scientific approach, therefore, is not to dogmatically rule out an extraordinary origin, but to systematically test the natural models until they either fully account for the observations or break down under the weight of new contradictory data. So far, the natural models, particularly the binary magnetar, are not only holding, but are being refined and strengthened with each new observation. The 16-day period is a powerful clue that fits beautifully into the framework of celestial mechanics, not information theory. It speaks of orbits and stresses, not messages. This grounding in natural physics, however, does nothing to diminish the profound awe the signal inspires. In fact, it enhances it. The universe has crafted, through the blind forces of gravity, nuclear fusion, and magnetic dynamos, a natural engine of such precision and power that it mimics the very clocks we build. This is a humbling and magnificent realization. The signal that repeats every 16 days is a testament to the fact that nature, in its most extreme laboratories, can produce phenomena of such ordered complexity that they border on the seemingly artificial, reminding us that the cosmos is capable of wonders that exceed our imagination without requiring our myths. Our task is not to project our stories onto it, but to decode the physical story. It is already telling a story written in the language of relativistic plasmas, quantum electrodynamics in supercritical magnetic fields, and the slow, graceful, and inescapable dance of two stellar survivors around their common center of mass. This decoding effort is now accelerating, driven by the predictive power of the period. The coordinated multi-wavelength campaigns during the active windows of FRB 180916 and other repeaters are the new frontier. Radio telescopes across the globe, from the Arecibo Legacy equipment to the Meerkat Array in South Africa to the deepspace network dishes, are synchronized to observe during these windows, hoping to catch bursts with unparalleled time resolution and polarization data. The polarization of the radio waves, how their electric fields are oriented, is a critical probe. As the burst propagates through the magnetized plasma of its host galaxy, the intergalactic medium, and finally the Milky Way, its polarization angle is rotated by an effect known as Faraday rotation. Measuring this rotation in exquisite detail can map the magnetic fields along the entire line of sight, turning each burst into a probe of the cosmic web's invisible magnetic skeleton. The periodic source gives us repeated opportunities to make these measurements, building up a statistical picture of a path 500 million light-years long. Furthermore, if the bursts originate from within a binary system, the polarized signal might carry subtle imprints of the local magnetic environment near the magnetar, perhaps even modulated by the orbital phase, offering another indirect window into the system's geometry. This patient, cumulative gathering of faint clues, a polarization measurement here, a possible faint X-ray photon there, a slight shift in the burst's frequency structure over time, is the slow, meticulous work of cosmic forensics. We are reconstructing a cataclysm that occurred 500 million years ago in a system we can never see directly, using only the faint, dispersed, and time-delayed echoes of its fury. The 16-day period is the steady drumbeat around which this entire symphony of observation is now organized, a gift of predictability in a field born from randomness. As the specific investigation into the rhythmic repeater continues, its ripples spread outward, influencing the grandest scales of cosmological inquiry, the very existence of fast radio bursts, and now our ability to predict some of them, has bestowed upon astronomy a potent new tool for mapping the universe's most elusive components, the missing baryons and the cosmic web's magnetic fields. For decades, cosmologists have faced a troubling inventory problem. When they tally all the normal matter, the protons, neutrons, and electrons that make up stars, planets, gas, and dust that they can directly see in galaxies and clusters, the sum falls woefully short of the total amount of normal matter predicted to exist by our gold standard model of the universe's evolution, based on the cosmic microwave background. A significant portion, up to half, is missing, believed to be hiding in a diffuse, hot, ionized gas that fills the space between galaxies, the warm-hot intergalactic medium, or WIM. This gas is too tenuous and too hot to emit detectable light, or absorb it in ways that are easy to spot with traditional telescopes. It is the universe's hidden backbone of normal matter. The fast radio burst, especially one with a known distance like FRB 180916, provides a near-perfect probe for this missing material. As the burst travels across the cosmos, its journey is not unimpeded. The sea of free electrons in the ionized plasma of interstellar, intergalactic, and circumgalactic media acts as a prism for radio waves. Lower frequency radio waves are delayed slightly compared to higher frequency ones, a phenomenon called dispersion. The total delay, measured as a smooth smear of the burst signal across frequencies, is quantified as the dispersion measure. This number is a direct count, a cosmic odometer, of the total number of electrons along the line of sight. By knowing the precise distance to the host galaxy 500 million light-years in the case of FRB 180916, astronomers can calculate the expected dispersion measure from known structures like the Milky Way's own 5 interstellar medium and the host galaxy's contribution. The excess, the remainder, must be due to the ionized gas in the intergalactic void. Each localized FRB, therefore, provides a single, precise measurement of the average electron content along one very long, very thin pencil beam through the cosmos. By collecting dozens, then hundreds of such measurements from FRBs at different distances and in different directions, we can begin to construct a three-dimensional map of the distribution of this missing baryonic matter. It is akin to using distant flashbulbs to illuminate the faint, wispy fog that fills a vast room. The periodic repeater, with its predictable activity, allows for even more precise measurements of its dispersion, as multiple bursts can be averaged and studied for subtle variations that might indicate the clumpy, filamentary nature of the WIM, tracing the cosmic web itself. Beyond simple electron counting, the polarization of the burst reveals the magnetic universe. As the polarized radio wave traverses magnetized plasma, its plane of polarization slowly rotates, an effect known as Faraday rotation. The amount of rotation depends on the strength of the magnetic field along the line of sight and the density of electrons. By measuring the Faraday rotation of an FRB and combining it with the independent dispersion measure, astronomers can, in principle, disentangle the magnetic field strength from the electron density. This offers the first realistic prospect of measuring the weak, primordial magnetic fields that are thought to be stretched across intergalactic space, fields that could hold the key to understanding the origin of the more powerful magnetic fields seen in galaxies and clusters. Did these fields grow from tiny seeds in the early universe? Or were they injected later by galactic winds and active galactic nuclei? Each polarized FRB is a probe sent through these fields, and the growing sample, anchored by reliable, localizable sources like the periodic repeater, is beginning to provide constraints. The signal that repeats every 16 days is thus more than a fascinating object of study. It is a calibrated lighthouse in the cosmic fog, its regular flashes providing a steady, reliable reference point in this new era of cosmological tomography. Its predictability allows for the most meticulous measurements, setting the standard against which other, more erratic bursts are compared. This transforms FRBs from mere cosmic curiosities into essential tools for fundamental cosmology, tools that can weigh the invisible stuff between the galaxies and feel the pull of its magnetic fields. This utility, however, hinges on a crucial step: accurately knowing the distance to the burst. This is why the localization and host galaxy identification of FRB 180916 was as critical as the discovery of its period. Without the redshift of the host galaxy, the burst is just a fascinating signal from an unknown distance, a clue without context. With it, the dispersion measure transforms from an abstract number into a precise column density measurement. The coordinated effort to localize repeaters has therefore become one of the most intense pursuits in observational radio astronomy, involving global networks of telescopes performing rapid response observations. The rhythmic nature of a source like FRB 180916 makes this coordination logistically feasible, turning what was once a game of chance into a scheduled experiment. This shift is emblematic of the entire field's maturation, from the serendipity of the Lorimer burst to the scheduled, targeted observations enabled by the ticking of a cosmic clock. As we look to the future, with next-generation radio telescopes like the Square Kilometer Array, SKA, coming online, the promise of this tool grows exponentially. The SKA will detect thousands, perhaps tens of thousands, of FRBs per year, many of them localized to their host galaxies. This vast statistical sample will allow us to map the three-dimensional distribution of cosmic baryons and intergalactic magnetic fields with a fidelity previously unimaginable. It will also undoubtedly uncover a menagerie of repeating behaviors, with periods ranging from hours to years, revealing the full diversity of the binary systems or other modulating mechanisms that can produce these bursts. In this coming flood of data, the first periodic repeater will be remembered as the pivotal proof of concept, the object that demonstrated that order could be found, that these signals could be predicted, and that their greatest value might not lie solely in explaining their own extraordinary origins, but in using their extraordinary journeys to illuminate the dark, vast, and invisible architecture of the cosmos itself. The quiet, patient rhythm, first discerned in the data from a fixed array in a Canadian valley, thus becomes a metronome for a much larger investigation, its steady tick now pacing our exploration of the universe's hidden masses and forces, a humble beat against which we can measure the fabric of everything. Yet, even as we project forward into a future of thousands of mapped bursts, the present mystery of the single, ticking source retains a deep and compelling pull. The very precision of the 16.3 five-day cycle invites a level of scrutiny so fine it begins to probe the limits of our understanding of time and stability in the cosmos. Is the period perfect? Does the cosmic clock keep perfect time? Or does it drift, however minutely, over the years? The answer to this question is a delicate probe of the system's dynamics and evolution. A perfectly stable period, invariant over decades of observation, would suggest an exceptionally clean, circular orbit with minimal gravitational perturbations from other bodies, or from effects like gravitational wave emission. But a detectable drift, a slight shortening or lengthening of the period, would be a treasure trove of information. A decreasing period could indicate the system is losing orbital energy, perhaps through gravitational radiation, causing the two stars to spiral inwards towards an eventual merger, a potential progenitor for a future gamma-ray burst or gravitational wave event. An increasing period might suggest mass transfer from the companion to the magnetar, or mass loss from the system via a stellar wind, processes that would push the stars apart. Monitoring this cycle with the patience of a geologist studying glacial movement is now a long-term project for radio observatories. Each new active window provides another data point, another tick of the clock to be measured against the ephemeris, the predicted times of arrival. This requires a vigilance that stretches across years, a commitment to listening for a whisper on a strict schedule, a practice that echoes the decades-long monitoring of pulsars that first provided indirect evidence for gravitational waves. The ticking of FRB 180916 has, in a sense, enrolled it in that elite cadre of celestial timekeepers, though its timekeeping is not of its spin but of its orbitally modulated fury. This long-term timing also opens a window into the life cycle of the magnetar itself. Magnetars are not eternal. Their monstrous magnetic fields are thought to decay over timescales of 10,000 years or so, as the energy is gradually dissipated in heating the crust and powering particle winds. As the magnetic field weakens, the threshold for triggering a starquake might change. The bursts could become less energetic, or the required tidal stress from the companion might need to be greater, potentially altering the pattern of activity within the 4-day window. Over human timescales, such changes would be infinitesimally small, but over centuries of theoretical observation, they might become discernible. The source we see today is a snapshot of a system in mid-evolution, a magnetar perhaps tens of thousands of years old, orbiting a star that may be millions or billions of years old. Their dance is a temporary one, on cosmic scales. Eventually, the magnetar's field will decay into obscurity, or the binary orbit will decay into a merger. The signal that repeats every 16 days is thus not a permanent feature of the universe, but a transient phase in a stellar relationship, a chapter in a longer story that we are fortunate to have tuned into. This perspective of catching a fleeting rhythmic phenomenon in the immense sweep of cosmic time adds a layer of poignant fragility to the investigation. We are witnesses to a process that occupies a narrow slice of deep time, a process that began long before human consciousness and will end long after our civilization is dust, yet whose regularity makes it feel eternal to our brief perceptions. This contrast between cosmic ephemerality and human-scale regularity is at the heart of the signal's quiet drama. It also forces us to consider the selection effect inherent in our discovery. We found this periodic repeater because its period is relatively short and its bursts are relatively bright and frequent. How many other such systems exist with longer periods, 100 days, a year, a decade, whose active windows we have simply not yet connected across the gaps in our observational history? The CHIME telescope, with its relentless, unchanging gaze, is uniquely suited to uncovering these longer periods, as it accumulates years of uninterrupted data on the same patches of sky. The discovery of the 16-day period was likely just the first and most obvious rhythm. Others may be hidden in the data, waiting for enough cycles to pass to reveal their pattern. The universe may be filled with such clocks, each ticking at its own pace, a cacophony of cosmic metronomes we are only beginning to hear. The search for these longer periods is an exercise in patience, a testament to the slow, cumulative nature of science, where answers are not found in a single brilliant flash, but in the painstaking connection of dots across years of silence. It requires a different kind of listening, one that is not startled by the sudden burst, but is attentive to the long spaces between, trusting that order may reside even there. This philosophical shift from reacting to the explosive to anticipating the rhythmic may be the most profound legacy of this discovery. It teaches us that behind the most violent and seemingly chaotic phenomena, there can be an underlying architecture, a geometry of cause and effect that is comprehensible. The starquake on the magnetar is not random. It is the inevitable consequence of stress applied by a companion in a predictable orbit. The burst is not an isolated scream into the void. It is a scheduled release of pent-up energy. In understanding this, we demystify the phenomenon, but we do not diminish its wonder. We transfer the awe from the unknown to the intricate clockwork beauty of known physics operating at its most extreme limits. The mystery of the repeating signal is thus being gradually transfigured from a "what if" into a "how exactly." The remaining questions are deeply technical, but no less profound for it. What is the exact equation of state of the neutron star crust that allows it to store and release energy in this way? What is the precise plasma instability in the magnetosphere that leads to coherent maser emission? How does the companion star's wind or magnetic field couple to the magnetar's magnetosphere? These are questions at the frontier of high-energy astrophysics and plasma physics. Questions that require blending general relativity, quantum electrodynamics, and magnetohydrodynamics in regimes no laboratory on Earth can ever recreate. The distant, ticking source is therefore a natural experiment, a running simulation of physics under conditions we can only dream of approaching. Our theories make predictions about the burst shapes, their polarization evolution, the potential for high-energy counterparts, and the source, with its reliable schedule, provides the testbed. Each predicted active window is an opportunity for the universe to confirm or refute our models, to provide a new piece of the puzzle. This iterative dialogue between prediction and observation is the essence of the scientific method, playing out on a stage 500 million light-years across, with a rhythm set by a 16-day celestial clock. The narrative of the repeating signal, however, is not confined to the sterile realm of pure physics. It is inextricably woven into the human endeavor of listening itself, a story of technology, patience, and the subtle art of discerning pattern from chaos. To appreciate the detection of the 16-day cycle is to understand the silent revolution in data processing that made it possible. The CHIME telescope, while revolutionary in its design, produces a torrent of data that would be impossible for humans to sift through directly. Every day, it receives petabytes of raw voltage readings from its antennas, a digital river of cosmic noise. The search for fast radio bursts within this river is the task of sophisticated algorithms, machine learning classifiers, and signal processing pipelines that run in real time, filtering out terrestrial interference from cell phones, satellites, and aircraft, and identifying the characteristic swept frequency signature of a dispersed pulse from deep space. Even after a candidate burst is identified, its significance must be validated. The discovery of the period in FRB 180916 was not a moment of eureka during a live observation. It was the result of months of accumulated detections, carefully cataloged, their timestamps stored in a database. The pattern emerged only after a sufficient number of points had been collected, after the statistical significance of the clustering crossed a threshold. It was a pattern found not in the sky, but in the curated archive of dates and times, a pattern that required a human mind, aided by computational tools, to recognize its simple, elegant shape against the background of randomness. This interplay between the vast, impersonal data collection of the telescope and the focused, interpretative insight of the researcher is the modern face of discovery. It is a quiet, collaborative process, often conducted in windowless server rooms or at cluttered desks, far from the romantic image of an astronomer at an eyepiece. The hero of this story is not just the telescope, but the pipeline, not just the observation, but the database. The 16-day period was always there, encoded in the arrival times of the bursts, but it remained invisible, latent, until the cumulative weight of evidence brought it into view. This is a profound metaphor for scientific understanding itself. The universe is speaking, but its language is often one of statistical correlation and subtle pattern, requiring long and patient listening before the grammar becomes clear. The detection also highlights the critical importance of the repeater phenomenon. A one-off burst, no matter how brilliant, offers only a single timestamp, a solitary data point from which no rhythm can be deduced. It is the repetition that allows for the collection of multiple points, the plotting of a light curve in time, the search for correlation. The repeater is a gift that keeps giving, a persistent subject that allows for follow-up, for deepening inquiry. In this sense, the original discovery of the first repeater, FRB 121102, was the pivotal event that made the discovery of periodicity possible. It proved that some FRB sources were not destroyed in the act, that they were persistent engines amenable to study. It transformed FRBs from ephemeral ghosts into objects that could be revisited, localized, and ultimately understood. The rhythmic repeater is the next logical step in this progression, demonstrating that not only can these engines persist, but their activity can be governed by a predictable external clock. This progression from one-off to repeater to periodic repeater traces a path of increasing comprehension, each step building on the last, each new class of object refining our questions. As we continue to listen, the next step in this progression may already be emerging: the detection of an FRB from within our own galaxy, ideally from a known magnetar, during a period of X-ray flaring. Such an event would provide the definitive smoking gun, linking the extragalactic phenomenon directly to a source whose properties we can study in much greater detail. The galactic magnetar SGR 1000, 935 plus 2000, 154 provided a tantalizing hint in April 2020 when it emitted a milliseconds-long radio burst that, while orders of magnitude less energetic than an extragalactic FRB, shared many of the same spectral and temporal characteristics. This event, detected simultaneously by CHIME and the STARE-2 telescope, was a watershed moment, strongly supporting the magnetar origin theory. But it was not a perfect analog. Its radioluminosity was far weaker. The search continues for a truly galactic event that matches the power of the extragalactic ones, which would require a magnetar even closer or an even more powerful flare. The periodic model suggests we should also be searching for binary modulations in the behavior of known galactic magnetars, looking for patterns in their X-ray or radio flaring that might betray the presence of an unseen companion, a silent partner in their violent outbursts. This work proceeds slowly, a meticulous reanalysis of decades of data from X-ray observatories like RXTE, Swift, and Fermi, searching for hidden clocks in our own backyard. Whether or not such a local, periodic FRB source exists, its potential discovery drives a significant part of the observational strategy, a reminder that the grand, cosmological story of FRBs is also a local one, with chapters yet to be written about objects that may be only thousands of light years away. This interplay between the local and the extragalactic, between the detailed study of known objects and the statistical study of distant populations, is what makes the field so dynamic. The rhythmic repeater sits at the confluence of these streams, a distant object that informs our search locally, and a predictable object that provides the cleanest data for cosmological probes. It is a keystone in the arch of understanding being built across this new frontier of transient astronomy. Beyond the immediate astrophysical and cosmological implications, the rhythmic signal invites a quieter, more reflective consideration of our place as listeners in a universe that is not silent, but whose languages we are only beginning to comprehend. For nearly all of human history, the night sky was a panorama of stillness, a fixed tapestry of points of light whose changes were gradual, cyclical, and predictable on timescales of seasons and millennia. The discovery of variable stars introduced a first note of change, but it was the advent of radioastronomy that truly opened our ears to a universe in constant, violent flux, a cosmos crackling with the static of synchrotron emission, the periodic ticks of pulsars, and the roaring jets of active galaxies. Fast radio bursts, and particularly this repeating, periodic one, represent a new dialect in this radio symphony, one characterized by extreme brevity, immense power, and now a haunting regularity. They remind us that the universe is not only vast in space, but rich in time, filled with processes that operate on timescales from milliseconds to eons. Our ability to detect a 16-day rhythm across a gulf of 500 million light-years is a testament to a specific kind of technological and intellectual maturity. It requires instruments sensitive enough to catch the fleeting whisper, data systems robust enough to store and cross-reference it over years. and a scientific culture patient enough to look for patterns that unfold not in a night, but over seasons. This is a different kind of astronomy from the instant gratification of a beautiful new image from Hubble or Webb. It is the astronomy of the ledger, the slow accrual of timestamps, the faith that significance lies in the connection of points separated by weeks of silence. It is, in a deep sense, a conversation with deep time. The signal we observe today left its source when the first complex animals were beginning to diversify in Earth's oceans, long before the age of dinosaurs. The rhythm we discern has been ticking away for 500 million years, uninterrupted by the rise and fall of continents, the oxygenation of atmospheres, or the birth of consciousness on a pale blue dot. There is a profound humility in this realization. We are eavesdropping on a process of such immense age and stability that our entire civilization is but a flicker in its timeline. Yet our science allows us to apprehend its logic, to predict its next pulse. This predictive power is perhaps the most human aspect of the endeavor. In a universe often governed by probability and chaos, finding a predictable clock satisfies a deep cognitive longing for order. It gives us a handle, a way to interact with the phenomenon, to test our ideas not passively, but actively, by scheduling our observations and waiting for the universe to confirm or deny our expectations. This transforms the relationship from one of passive observation to one of engaged dialogue. We are no longer just recording cosmic accidents. We are conducting scheduled interviews with a distant, extreme physical system. This engagement has a unifying effect on the global scientific community. The predicted active windows of FRB 180916 are known to all. They are published, shared, and become focal points for coordinated observing campaigns that span continents and telescope architectures. Radio dishes from Europe to Asia to the Americas can be pointed in unison, creating a virtual telescope of global extent to dissect a single burst. X-ray and optical telescopes in space and on the ground are alerted to point at the coordinates during the window, hoping to catch a counterpart. This worldwide, synchronized effort, all orbiting the schedule of a tiny object in a distant spiral arm, is a remarkable feat of human cooperation, driven by shared curiosity. It is a modern version of the ancient practice of gathering to observe an eclipse, but now the participants are distributed across the globe, and the predicted event is not the shadow of our own moon, but the scheduled fury of a star that died eons ago. The rhythmic repeater has thus become a celestial rallying point, an object that not only advances astrophysics, but also demonstrates the collaborative, borderless nature of fundamental inquiry. It serves as a reminder that the most intriguing puzzles of the cosmos often require a collective, patient, and globally distributed intelligence to solve. And yet, for all this collaboration and technological prowess, a fundamental solitude remains. We are listening, but we are not being addressed. The signal, for all its intriguing structure, carries no message beyond the physical parameters of its emission and propagation. Its meaning is not semantic, but physical. It tells us about magnetic field strengths, plasma densities, orbital mechanics, and the distribution of matter in the cosmic web. Its value is not in what it says, but in what it is. This is the essence of pure science, finding meaning in the intrinsic nature of phenomena, constructing understanding from the bottom up, from the measurable quantities to the underlying laws. The rhythmic FRB is a perfect exemplar of this process. It offers no wisdom, no warning, no greeting. It simply is. And in its stark, regular existence, it poses questions that lead us deeper into the fabric of reality. This journey, from a curious timestamp in a database to a reshaping of our understanding of magnetar binaries and our mapping of the cosmic web, is a narrative of human rationality at its best, a narrative driven not by fear or fantasy, but by a calm, persistent desire to know. The signal that repeats every 16 days is therefore more than an astrophysical object. It is a mirror reflecting our own capacity for wonder, our ingenuity in toolmaking, and our relentless pursuit of patterns in the dark. It is a beacon, not of other intelligence, but of the intelligibility of the universe itself. A reassurance that even in its most extreme and distant corners, the cosmos operates by rules we can, with patience and care, come to understand. As the narrative of the rhythmic repeater finds its place within the broader tapestry of cosmic knowledge, it is essential to turn our gaze forward, to consider the trajectories of discovery it has set in motion, and the new instruments being conceived in its spectral wake. The established story of a magnetar in a binary system, its crust periodically stressed into starquakes that unleash coherent radio beams, is a powerful framework, but it is not the final word. It is a scaffold upon which more detailed and exotic theories can be built, and a benchmark against which future anomalies will be measured. The next phase of inquiry will be driven by an ever-increasing volume of data from current telescopes, and, more profoundly, by a new generation of observatories designed with the transient, rhythmic universe in mind. Projects like the Deep Synoptic Array in California, with its hundreds of dish antennas, and the full square kilometer array, to be built in South Africa and Australia, will detect FRBs not by the dozens, but by the tens of thousands. In this coming deluge, the search for periodicity will move from manual, single-source investigations to automated, systematic surveys of all repeating sources. Algorithms will continuously scan the growing databases of burst arrival times, searching for hidden frequencies, for modulations within modulations. We may discover sources with multiple periods, hinting at triple systems or precessing orbits. We may find that the periodic activity itself is episodic, that the clock winds down for a time, or that the period evolves in complex ways due to dynamic interactions with a circumstellar disk. The rhythmic repeater has provided the template, proving such searches are worthwhile. The future will reveal the full diversity of this temporal zoo. Furthermore, the push for multi-messenger astronomy will intensify. The coordinated campaigns for X-ray and optical counterparts will continue, but will be joined by efforts to link FRBs to other cosmic messengers. Could a particularly powerful magnetar starquake, one producing an FRB, also generate a detectable burst of gravitational waves? The current generation of LIGO and Virgo detectors is not sensitive to the high-frequency kilohertz waves expected from crustal fractures, but next-generation gravitational wave observatories in space, like the proposed Laser Interferometer Space Antenna, LISA, or more advanced ground-based detectors, might one day have the capability. The detection of a neutrino, or shower of neutrinos, coincident with an FRB, would be a direct probe of the hadronic processes in the magnetar's atmosphere, revealing whether protons or heavier nuclei are also accelerated in these events. The predictable windows of periodic repeaters offer the only feasible chance to conduct such searches, as the instruments can be put on high alert during these specific, limited times, dramatically improving the sensitivity of a coincident detection. The rhythmic source thus becomes a pivot point for the entire multi-messenger enterprise, a scheduled appointment for the universe to potentially reveal its secrets through more than one channel. On the theoretical front, the model will be stress-tested by numerical simulations of ever-increasing fidelity. Global magnetohydrodynamic simulations of a magnetar's crust and magnetosphere, coupled to the tidal forces of a binary companion, are among the most computationally demanding problems in astrophysics. They require modeling matter at nuclear density, magnetic fields, a quadrillion times Earth's, and relativistic plasmas, all in a dynamic, evolving geometry. As supercomputing power grows, so too will our ability to simulate not just the trigger, but the full chain of events from crustal crack to the generation of the coherent radio beam millions of kilometers above the surface. These simulations will make specific, testable predictions about the polarization patterns of the bursts, how they might change throughout the active window, and the potential for very high-frequency radio emission. Observers will then take these predictions back to the rhythmic repeater and others like it, checking the virtual universe against the real one. This iterative cycle of prediction and observation, powered by both increasing data and increasing computational might, is how a solid understanding is forged. The story of FRB 180916 is therefore transitioning from one of discovery to one of detailed characterization and exploitation. It is becoming a known source, a calibrator, a Rosetta Stone for deciphering the more cryptic members of its class. Yet, the history of astronomy suggests that the most profound revelations often come from the outlier, the object that does not fit the established pattern. So, even as we study this rhythmic repeater in ever finer detail, we must remain alert for the signal that breaks all the rules of repeater with a period that is not constant but chaotic in a mathematically strange way, a burst that carries an unexpected polarization signature, or a source that appears to originate from a galactic environment where no magnetar should exist, like a globular cluster or an elliptical galaxy devoid of young stars. The discovery of the 16-day period did not close the book on FRBs. It opened a new chapter where the questions are more refined, and the potential for surprise, though narrowed in scope, remains ever present. The ultimate goal is a complete taxonomy of FRB progenitors, a causal map linking the observed properties of a burst, its dispersion, rotation measure, repetition pattern, periodicity, host galaxy type to the specific physical engine that produced it. In this taxonomy, the binary magnetar model, exemplified by the rhythmic repeater, will likely occupy one major branch. Other branches will belong to the isolated magnetar flares, the neutron star mergers, and perhaps engines not yet dreamed of. The rhythmic repeater is the first member of its branch to be clearly identified. Its periodic nature, the defining trait that allowed us to trace its lineage. As we find more of its kin, with different periods and different burst properties, we will fill out this branch of the family tree, understanding the range of orbital parameters, companion types, and magnetar ages that can lead to this remarkable, scheduled phenomenon. In the final contemplation, the signal that repeats every 16 days transcends its identity as a mere astrophysical object and becomes a symbol of the evolving relationship between humanity and the cosmos. For millennia, we observed the heavens as a static clockwork, a realm of perfect, predictable cycles that governed our lives and calibrated our myths. The discovery of cosmic violence of supernovae, gamma-ray bursts, and colliding galaxies shattered that placid view, revealing a universe of catastrophic change and seething energy. The fast radio burst initially appeared to be the epitome of this chaotic violence, a millisecond scream from the void, utterly random and inexplicably powerful. But the discovery of its repetition first, and then its precise periodicity, wove these two narratives, the cyclic and the catastrophic, into a single, profound truth. The universe is both violent and orderly. Its most energetic explosions can be governed by the gentle, patient rhythms of orbital motion. The rhythmic repeater is the synthesis, a beacon of scheduled catastrophe. It tells us that the cosmos operates on multiple, intertwined timescales, the slow, gravitational waltz of two stars over weeks, and the near-instantaneous, magnetic detonation on the surface of one of them that lasts only milliseconds. Our ability to connect these scales, to see the link between the grand orbital dance and the fleeting radio flash, represents a significant maturation in our cosmic understanding. We are no longer intimidated by the violence, nor are we satisfied with merely cataloging the cycles. We are learning to see the causal chains that bind them together. This understanding carries a quiet, philosophical resonance. It suggests that even in the most extreme environments, where forces dominate that are utterly alien to our terrestrial experience, there is a logic that is comprehensible. The laws of physics, as discovered in our laboratories and through our observations of nearby space, appear to hold firm even halfway across the observable universe, under conditions we can only extrapolate to in theory. The rhythmic repeater is a test of that extrapolation, And so far, it holds. This is a powerful affirmation of the universality of physical law, a cornerstone of the scientific worldview. The signal, in its perfect regularity across 500 million light-years, whispers of a cosmos that is not arbitrary, but deeply structured and knowable. Our journey with this signal is also a lesson in epistemic humility and patience. The pattern was not apparent in the first burst, or the 10th. It revealed itself only after many cycles, after a commitment to continued observation, and a willingness to sift data for subtle correlations. Modern astronomy is increasingly dominated by such long-term, monitoring-based science, where discoveries are made not in a single night at the telescope, but over years in the data archive. It is a science that rewards persistence and collaboration, qualities embodied by the global networks of telescopes, and researchers now focused on this one source. As this story concludes, the signal itself does not. It continues its cycle, unaware of the telescopes trained upon it, the papers written about it, or the human minds it has captivated. It will likely continue for centuries, millennia, perhaps until its orbital period decays, or its magnetic field fades. It is a permanent or near-permanent feature of the radio sky, a new kind of celestial landmark. For future generations of astronomers, it may become a standard, a test source for new instruments. Its period so well measured it is used to calibrate clocks. It will have made the transition from a shocking mystery to a well-understood tool, a familiar part of the cosmic landscape. Yet, for us, in this moment of discovery and unfolding comprehension, it retains the glow of the new. It is a reminder that the universe still holds profound surprises, and that these surprises often come not as answers, but as better questions. The signal that repeats every 16 days asked us, what natural engine can produce such precisely timed fury? We have constructed a compelling answer, a magnetar in a binary embrace, but in doing so, we have been led to new questions about plasma coherence, crustal physics, binary evolution, and the distribution of matter in the cosmic web. Each answered question begets new, deeper ones. This is the endless, generative process of science. The quiet drama of this signal lies in this very generativity. It began as a point of data, a blip in a vast river of noise. Through human curiosity and ingenuity, it became a window into the heart of a star, dead and magnetized, a probe of the invisible threads between galaxies, and a testament to the ordered violence that sculpts the cosmos. It is a story that begins in a colossal explosion, finds its rhythm in a gravitational dance, and finds its meaning in the silent, patient act of listening across the ages. The universe is speaking in rhythms we are only now learning to hear, and in the quiet, insistent tick of this distant clock, we find both a profound mystery and a profound connection to the intricate, lawful, and majestic whole.